So in the previous video, we talked about the fact that gases exert pressure on their container as being one way that gases are fundamentally different from the other states of matter. And our goal for this video is understanding what factors affect the pressure of a gas. So we know that pressure is due to gas particles colliding with the walls of the container. So what we're really looking for here is how do we affect the frequency or intensity of collisions between gas particles and the walls of their container. So really there are three factors that we're going to be talking about. The first of which is the number of particles in the container. So for each of these factors, when we're discussing it, we're kind of assuming everything else is being held constant throughout to isolate the effect of just this one factor. So number of particles, specifically moles of particles, is what we're talking about. As chemists, we are usually thinking in moles, and moles of stuff is symbolized with the lowercase letter n. So essentially, in general, if all other things are held constant, more particles is going to lead to higher pressure. And that should make some sense if we think about the basis for pressure as collisions. If you have some container and you put more stuff inside of it, things are going to be bouncing off the walls more often. And that is exactly why increasing the number of particles in your container increases the pressure. More particles means more frequent collisions with the walls of the container. So as the moles of gas in a sample increases, the pressure also increases. So moles and pressure are what we call directly related. Which means that as N increases, P also increases. Or as N decreases, P also decreases. So however one changes, the other changes in the same direction by the same factor. So if N is doubled, P is doubled. If N is halved, P is halved. So basically the same thing happens to both. So mathematically speaking, we can express this as P over N or N over P, doesn't matter which way you think about it, is going to be equal to a constant. So if we know the pressure of some sample, let's say that 1 mole sample of some gas has a pressure of 1 atmosphere. Atmospheres is how we usually measure atmospheric pressure and the most common pressure unit used in the chemistry lab. If 1 mole has a pressure of 1 atmosphere, if we have 2 moles of gas under exactly the same conditions, that's going to have a pressure of 2 atmospheres. So these two things are directly related, and we can essentially think of them as a ratio that is always going to be constant. The second factor is the volume of our container. And we use capital V for volume. So if we decrease the volume of our container, let's think about what that's going to do in terms of collisions at the molecular level. So if we have particles in some largish container bouncing around. They're going back and forth between the walls every so often, moving at some speed. If all of a sudden my container is half the size and they're moving at the same pace, they're going to hit the walls twice as often because they don't have as far to go. They're going to hit the walls more frequently. So that means we're going to get more collisions and therefore more pressure. So decreasing the volume means you are increasing the pressure, again, if everything else is held constant, talking now about the same number of moles of gas under the same conditions. So again, thinking from that collisions perspective, if the walls of the container are closer together, if you just kind of simplify it as, bouncing back and forth in a straight line, particles will collide with walls more often. So we know that as volume goes down, pressure goes up. So we see these going in opposite directions, which means that these two things are inversely related. So as volume increases, pressure decreases. As volume decreases, pressure increases. So they go in opposite directions in this case. So mathematically, we can express this as the product of pressure and volume is going to be constant. That if I double my volume, my pressure is going to be cut in half. So they're being changed by the same factor, just in opposite directions. If the volume is multiplied by 2, the pressure is divided by 2, or vice versa. But the product of these will be constant because of this inverse relationship. The third and final factor that we're going to talk about is temperature. So temperature is symbolized with a capital letter T. And before we can really talk about how temperature affects pressure, we need to understand more about what temperature is really measuring at the molecular level. So temperature is actually a measurement of kinetic energy in a substance. And kinetic energy is often referred to as the energy of motion. For a particular object or a particular substance, the faster it is moving, the more kinetic energy it has. There's also a relationship between mass and kinetic energy. But if you're talking about the same substance, the mass is going to stay constant. So it's just as the kinetic energy changes, the speed is changing. So when we're measuring temperature, we're measuring the kinetic energy of particles. So as the temperature is changing for those particles, the speed is changing. So if the temperature of a substance or a sample increases, what that means is at the molecular level, the particles are moving faster, they're speeding up. So if we think about temperature from this perspective and kind of switch back into how does this affect pressure in terms of the collisions with the walls of the container, moving faster means your particles are going to hit the container more often. And because you're moving faster, your particles are also hitting harder. If they come in really slow and like bounce off, that's a sort of weaker collision. If they're moving faster, they're going to hit harder, which is also a factor in pressure as well. So particles collide with the container more often and hit harder as well. So that is increasing our pressure. So as temperature increases, our pressure increases as well. And of course, the opposite is also true. As our temperature decreases, the particles are moving more slowly. They're not hitting the walls as often. They're not hitting the walls as hard, so our pressure decreases. So temperature and pressure go in the same direction. They either both increase or both decrease. So we can say that temperature and pressure are directly related. So mathematically, we can think that P over T or T over P, either way, same effect, is going to be equal to a constant. So one other thing to keep in mind with temperature is that we know there are multiple different temperature scales. You are almost certainly familiar with Fahrenheit because it is what we usually use for weather and such here in the US, as well as Celsius because that's what we use most of the time in science. But when we're dealing with gases and certain other types of calculations in chemistry, we need to use the Kelvin temperature scale. In order for our calculations to turn out correctly. So if you need to convert between Celsius and Kelvin, Kelvin temperature is just the Celsius temperature plus 273. So you will want to be comfortable with that conversion factor. The reason why we need to use Kelvin is that Kelvin is the only temperature scale where the numerical value of the temperature is actually related to the kinetic energy, and we're using temperature very much as a measurement of kinetic energy here. 0 Kelvin is known as absolute zero, is the temperature at which all molecular motion stops, which would mean that the particles have 0 kinetic energy. So 0 Kelvin corresponds to 0 kinetic energy, and then things kind of scale up from there. So the Kelvin temperature has a meaning more based in physics, which is why it's important that we use that one in these types of calculations.